So informally, a path is a sequence of edges that begins at a vertex, travels from a vertex to another along certain edges of the graph. As the path travels along its edges, it visits the vertices along this path, that is the end point of the edges. Now the definition says that, but a bit formally. But in there, there's what's known as a circuit. So let me read that really quick, the part up there. Let n be a non-negative integer and g an undirected path. A path of n from u to v in g is a sequence of n edges e1 through e sub n of g for which there exists a sequence. So kind of like the mathematical, pretty much that's what I just read up there, of vertices. The important part is for us to figure out certain parts. So let's specify. The path is a circuit if it begins and ends at the same vertex. That's like closed. If u equal v, that is, if u equal v and has length greater than 0, the path or circuit is said to pass through the vertices x1 through x sub n or traverse the edges. Either way, a path or circuit is simple if it does not contain the same edge more than once. Basically, you do not cross yourself. There's a remark there, they talk about this is really like walking around instead of thinking as edges. You start at point A and you walk to B, then you walk to C, you walk to D, and so on and so forth. Kind of like walking a trail. Now, we have another definition here of what a path is. Well, let n be a non-negative integer and g be directly graph. A path of length n from u, v, n. So the same basically definition as beginning is associated with x1, x2, and so on, and this is with x. So they're making this more mathematical. When there are no multiple edges in a directed graph, this path is denoted by its vertex of sequence. A path of length greater than 0 that begins and ends at the same vertex is called a circuit or cycle. The same deal. A path or circuit is called simple if it does not cross its edge more than once. And the terminology here, they tell you what these apply in. Now, an undirected graph is called connected if there is a path between every pair of distinct vertices on the graph. An undirected graph is a graph that's not, an undirected graph that is not connected is called disconnected. We say that we disconnect a graph when we remove a vertices or an edge or both to produce a disconnected subgraph. There is a simple path between every pair of distinct vertices of a connected undirected graph. A directed graph is called strongly connected if there's a path from A to B and there's a path from B to A. A directed graph is weakly connected if it is connected, if there is a path between every two vertices in the underlying undirected graph. So there is, but there isn't one coming back. You could go from one, not to the next. This one I'm going to leave alone. This deals with, I might need that in 10.5. I'll come back to it. This is writing those paths as a matrix. We already know how that works. So let's start with some problems. This is on page 724. So let's see if we could follow on and see how this works. It says, does each of the lists of the vertices from a path in the following graphs, which paths are simple, which are circuits, what are the length of those that are paths? Well, let's see. If I look at A, B, so let's see, A, B, E, C, B. Yeah, that works. The length is 4. This is not a circuit. And why is that? Well, it started with A, it didn't end And this is simple. Why is that? Because no edges repeat. Look at the edges. We went 1, 2, 3, 4. All right? And not a circle because you didn't. Okay, we said that already. How about B? Let me reset this again. B says start with A, go to D. Oops. Then go to A. Okay, very good. Then go to D. Then go to A again. Okay, well, the length is 4 as well. This is a circuit. Why? Because it starts with an A and ends with an A. Oh, I'm sorry. That was this one. And it is not simple. And why is that? Well, you could tell. You went down, then back up, then you went back down. You used the same edge twice. And how about C? C has A to D, A to D, and D to B. There's no path, so this is not a path. No edges from D to B. And how about D? Let's reset this. D, we start with A, we go to B, then we go to E. Well, same deal, we can't go to E. A, B. Oh, wait a minute. Wait. I think I messed up. A to B, I'm up there. To E, there is E. To C, to B, to D. Yeah, I wrote that in my notes. There's no path there. All right. If I look at number 4, it says determine whether the given is connected. Remember what connected was, and it's right there. An undirected graphs go connected if there's a path between every pair of distinct vertices. Well, let's see. Is there a path between all of these? Let's see. That works. I could have also went this way, this way, this way, this way, this way. So pretty much I can connect everything. So yes, this is connected. There is a path between there's a path for every from vertex to every other vertex. So you just need a path. You need to be able to reach all of them. Number 6. How many connected components does each of the graph have? Well, let's see. There's 1, there's 2, there's 3. Here, for each graph, find each of its connected components. Well, these are the components, those, and that by itself. So there's 3 of them. And how about here? We have 1 component, and this is connected. And how about here? We have 2 components, right? The 2 triangles. There's 1, and there's another. Here, there's 1, there's 2, there's 3. But here, there. Oh, what just happened? Okay, how about the following? Determine whether each of these graphs is strongly connected, and if not, whether it is weakly connected. So if they are connected, if there's a path, between them, they're weakly connected. But if there's a path from A to B and from B to A, then this is called strongly connected. Well, let's see how this works. I'm looking at A. This is connected for sure. I could go from A, I could go from any of those vertices to another, but it's not strongly. So this is weakly connected. And why is that? Because I can go from A to B, but I can't go, I go from A to F, I can go from F to A. Here, A to B, B to C, so we have a path, you go A, B, C, D, E, F, and come back. You go from B, you could go, yeah, you go from each one of those, you go all around and come back. So this is strongly connected. And obviously, if it's not connected, it can't be strongly or weakly. There we go. And if I look, well, this is definitely not connected, because D to B, we don't have one. Or you could write B does not connect to D. Or F. Use path either to show that these graphs are not isomorphic, or to find an isomorphism between the graphs. Well, 3, 3, 3, 3. So I could say I could take U1, U2, U6, U2, and U1. Right? That's a simple closed path. But here, there's no way of doing that. There's no way of using the 3, because if I go from V1 to V5, there's no way of reaching V7 without crossing another path. So those are not isomorphic. And that's pretty much it for this section.